Alrighty, welcome back. We are jumping into section 6.3. 6.3 is proving quadrilaterals, quads are parallelograms. Remember, that's my shorthand way of saying parallelograms. Don't put that on a standardized test because they're not going to know what you're talking about. In the start thinking part, we discuss what we learned in 6.2. In 6.2, we were working with some conditional statements. The conditional statements said if the quadrilateral is a parallelogram. So that was if you already knew it was a parallelogram, then we knew a few different things were true. Number one, both opposite sides would be parallel. Number two, both opposite sides would be congruent. Number three, A and B would be sup and B and C would be sup. Consecutive angles are supplementary. The next one was that both opposite angles are congruent. And then the last one was that if you drew the diagonal and you drew the other diagonal, they would bisect one another. So those would be congruent, and these ones would be congruent. Not necessarily all congruent to one another, but this one, if this was 5, then this one would be 5, and if this was 3, let's say, then that would be 3. All right, so this was the conditional statement knowing that it was a parallelogram. Now what we're going to do is figure out how to prove something as a parallelogram. Now, if you think back to chapter, I think it was 2, when we were trying to prove lines were parallel, before we had proved lines are parallel, we knew that they were parallel. And if we knew where they were parallel, then the alternate interior angles were congruent, the same side interior angles were supplementary, corresponding angles were congruent, and all that. So that was, you already knew that they were parallel. Then the next section, what we did is we learned how to use the converse of the different theorems. The converse was if you knew that these angles were congruent, you could use the converse to say that now you know the lines are parallel by the converse of, let's say in this one, the alternate interior angles theorem. Okay. So now what we're going to be doing is here was the original conditional statement, and we are going to be seeing if the converse of all those is also true. We're going to prove some of them, and some of them we're just going to write down. So the first one is looking at if both pairs of opposite sides of a quadrilateral are congruent, then the figure is a parallelogram. So one way to prove that something is a parallelogram is knowing that both opposite sides are going to be congruent. And what I'm going to do is I'm going to look over the proof, but I am not going to actually write out the whole entire proof. We're just going to talk about it. So let's say we had this. I'm going to scribble that out just so that we can label this as A, B, C, D. Okay, so what would be given is that that is congruent to that and that these are congruent, and somehow we need to prove that this is a parallelogram. Well, step one would be going over and drawing this in. If you drew this in, then you would have two triangles. With those two triangles, you would be able to use the reflexive property. After the reflexive property, you can see the two triangles would be congruent by S, S, S. Why would I care about that? Well, if the two triangles are congruent by SSS, what do we know about these corresponding angles? Well, we would know we could use CPCTC to show that corresponding parts of congruent triangles are congruent. Now I know that an angle is congruent to an angle. Now, why do I care about that? Just look at this again. We're basically saying that that angle is congruent to that angle. If those angles are congruent, then what do we know about the top and the bottom? The top and the bottom are parallel by the converse of the alternate interior angles theorem. Okay. Now what we would do is we'd go over and state that these ones were congruent by CPCTC. So by CPCTC, the other angles are congruent. Why do I care about those angles? Because if I drew this and I was talking about that angle being congruent to that angle, then once again, I know now the left and right are going to be parallel by the converse of AIA. And once I know that both pairs of opposite sides are parallel, then it must be a parallelogram by def of parallelogram. So I'll go through this one more time. We use the reflexive property. I guess I could write that too. Remember, this is not a good proof. Like, this is not an actual flow proof. This is just a thought process. A flow proof would have to have more stuff there. The reflexive property is that middle part. And then that leads you to know that the triangle is congruent to the triangle by SSS. By CPCTC, we now know that that angle is congruent to that angle, which leads us to know the top and bottom are parallel. Then this angle is congruent to this angle by CPCTC, which now tells you that the left and the right are going to be parallel. And then when you know both pairs of opposite sides are parallel, then you know you have a parallelogram. We didn't write out a pretty proof, but we know our logic is sound because we studied proofs, and we know everything I just listed there in my logical reasoning is based off of a theorem or a postulate. All right, I hope that made sense. So now we know one of the ways to prove something is a parallelogram. Do you have to go through this whole process? No. Now you know if both opposite sides are congruent, then you can state that it's a parallelogram because we already did a proof, and that proof leads to us knowing that it's a parallelogram. The next one we're going to look at is if the consecutive angles are supplementary. So if the consecutive angles of a quadrilateral are supplementary, then the quad is a parallelogram. Okay. Once again, we're going to talk through the logical reasoning, but I'm not going to actually write out the whole entire proof. Let's call this angle A, B, and C. And our given is that A and B are going to be supplementary and B and C are going to be supplementary. So let's go through this. If A and B are sup, then I am going to know the top is parallel to the bottom. How am I going to know that? Because think about that. What type of angles are A and B? They're SSIA. So that would be the SSIA postulate. Next one, if B and C are sup, which is one of the things we are assuming is true, that's our hypothesis, then we would now know, think of this and that, and here's the transversal. B and C are SSIA as well, so this would make it so that the left is parallel to the right, also by SSIA postulate. And if the top and bottom are parallel and the left and right are parallel, then it is going to be a parallelogram by def of parallelogram. Really, the only person you should use this notation with is me. Anybody else is not going to know what that means. Once again, just write out the word parallelogram otherwise. But if it's me, I know that that's the symbol for parallelogram. Great. All right, so now we have two different ways to prove that a figure is a parallelogram. One is if you know both opposite sides are if you know both opposite sides are congruent, that's one of the ways. And the other way is if all consecutive angles are supplementary. And we went through the logical reasoning behind that right here. Ta-da! Let's move on to the next page and see what else we've got. Okay, the next one we're going to be looking at is if the opposite angles of a quadrilateral are congruent. But here's the thing, if both, please put this in, both pairs. It has to be both pairs, okay? It can't just be one. Let me show you an example of something that would have one pair, but it's not a parallelogram. Think about a kite. This would be your counterexample here. A kite would have one pair of opposite angles that are congruent, but it is not a parallelogram. So it's got to be both pairs of opposite angles of a quadrilateral are congruent. Then the figure is a parallelogram. Okay. Now let's go ahead and run through this proof because they made it nice and easy, and it's just a fill in the blank proof. So if we look at this and we're trying to figure out how they're doing it, well, what they do is they say if this is x, then this is going to be x as well because those are congruent. If that's y, then this is y as well. And they said that x plus y plus x plus y equals 360. Do you agree with that? That would be the sum of interior angles of a quadrilateral. N minus 2 times 180. 4 minus 2 times 180 gives you 360. Now what they do is they went over and factored. Okay, so they factored this to say that there are 2x plus y's. That's how you got from here to here. The book sometimes calls that combining like terms. I call it factoring. Okay, now the question becomes, how did we get from here to here? Looks like they got rid of the 2 by dividing by 2 and dividing by 2. Division prop of equality. Remember, you have to have a prop of equality because it's happening on both sides. Next, how do we know that angle A and B are supplementary and A and D are supplementary? Well, if we look at this, we know right here, we said that they add to be 180. So why are they supplementary? Definition of supplementary. Do you see angle A and B are the X and the Y, and they're saying they add together to be 180? Cool. And then they said that they were supplementary. So that's just definition of supplementary. Okay. Once we get here, we have B is supplementary to A and D is supplementary to A, right? So now, what do we do from there? If you know that A and B are supplementary, then that would lead us to know that BC is parallel, the top is parallel to the bottom, and we would also know by the other one that the left is parallel to the right, and that is by the converse of SSIA postulate. And then if you know both pairs of opposite sides are parallel, then you end up with a parallelogram by def of parallelogram. I wrote it all the way out. So that's a nice long proof. Once again, you knew that all the 2 x's and the 2 y's are going to add to be 360 because it's a quadrilateral. Then you factored, then you divided by 2, and that led you to know that the 2 angles are going to be supplementary and the other 2 angles are supplementary. Therefore, the top and the bottom are parallel and the left and right are parallel by converse of SSIA, and therefore it's a parallelogram. Getting your healthy dose of proofs here. All right, let's look at the next one. The next one says if the diagonals bisect one another, then what do you think? The figure is a parallelogram. So if you knew that that was congruent to that, and that's congruent to that, then it is definitely going to be a parallelogram. Let me quickly show you. Once again, we're not going to do the whole entire proof. But let's say we had this, and we knew that that was congruent to that, and this is congruent to this. What I can do is now use the vertical angles theorem, and now you know the 2 triangles were congruent by SAS. Since the 2 triangles are congruent by SAS, then now I would know that this angle, let's see, this angle would be congruent to this angle by CPCTC, CPCTC, angle congruent to angle. And then by CPCTC, I would also, actually that would be as much as you could do. So now you would know that the left is parallel to the right by the converse of AIA. Now you kind of actually have to do it over again. So you go over, and now instead of working with the left and right triangle, you'd work with the top and bottom triangle. So once again, they'd be congruent by SAS, which would lead you to knowing the angle is congruent to the angle by CPCTC. And now you know the top is parallel to the bottom by the converse of AIA again, because now we would know that that angle was congruent to that angle. So you basically have to work with two different pairs of triangles. And that is the logical reasoning, which is backed up by theorems. So it works. Okay. And then once again, that would finish by saying it's a parallelogram by definition, a parallelogram, because now you know it has two pairs of parallel sides. All right, let's finish this puppy up. Okay, we have one last one. This one last one has to do with one thing that doesn't really correlate perfectly to 6.1. So on here, what this says, if one pair of opposite sides are both parallel and congruent. So if the top and bottom were parallel and congruent, or the left and right were parallel and congruent, it has to be the same sides that are both parallel and congruent, then the figure is a parallelogram. Basically, how we would do this is you already know that these ones are parallel, so all you have to do is show the left and right are parallel. So you would basically make these into two triangles. You would have that's congruent to that by alternate interior angles theorem. You have the reflexive property. So now the two triangles would be congruent by SAS. And if the two triangles are congruent by SAS, now we would know that that angle is congruent to that angle by CPCTC. Therefore, by converse of alternate interior angles, those are parallel, and therefore it's a parallelogram. So that's the concept behind the proof, right? Once again, you need to know it's the same sides. If it's these sides that are congruent, those ones have to be parallel. If it is these ones that are parallel, then they also need to be congruent. All right. Now, basically what we're going to do here is we're going to look at these and we're going to try to figure out if there's enough information to say that we have a parallelogram, and then try to explain why. So when you look at this, it looks like this angle is congruent to that angle, which leads me to believe that these are parallel. And then it says that those are congruent to those, which tells me those are parallel. So yes, this is a parallelogram. And what is the reason? Just definition of parallelogram. Wasn't any of the other ones, it was just the fact that we knew both pairs of opposite sides were parallel. Take a look at this. If this is 50 and that is 130, those are SSIA. If those are SSIA and it looks like they add to be 180, then what do we know about the top and the bottom? The top and the bottom must be parallel because of the converse of SSIA. Well, now, how do we finish this? We know all the ways we can prove that the two, or that the figure is a parallelogram. Look, they are congruent and they are parallel. So yes, it is a parallelogram because both parallel and congruent. One pair of opposite sides. I wouldn't expect you to do a full proof. You could just say, yes, it is because of this. Now the next one, on this one right here, tempted to say yes because the opposite sides are congruent, both opposite sides, but look, that one is congruent to this one, and that one's congruent to that one. I can show you a counter example like this. Congruent, congruent. That's a kite. So this, not enough information. I might even just say, no, it's not a parallelogram, because I can't think of a way that you would have a parallelogram. Because if these are congruent and then we use two different tick marks here, then those obviously aren't congruent. So I would just say that's a no. Okay, on this one, oh, look, they're congruent and they're parallel. So it's the same as this one, right? Nope, no. And if I had to give a reason, it's not the same two sides that are both parallel and congruent. So that's a no. All right, let's see if we have anything else here. Yep, just a few more. Okay, these are silly. I'm not even going to do them because all it says is, what are the values of x such that this would have to be a parallelogram? Well, we would know that that would have to be congruent to that, and this would have to be congruent to that one. But that's pretty much the same stuff we did in 6.2, so it's kind of a waste of time. I don't really think we need to do that. I'd rather take my last few minutes to go over this. This is the summary, okay? So the summary says, if you know both pairs of opposite sides are parallel, and that would be just the definition of parallelogram. If you know both pairs of opposite sides are parallel, then it's a parallelogram. The other way is show both pairs of opposite sides are congruent. Notice they have the word both. It can't just be one pair of opposite sides. So this would be enough to show that it's a parallelogram. On here, show that an angle is supplementary to both of its consecutive angles. Show that that's sup to that and sup to that. And once you are there, then it's a parallelogram. Don't worry about these. What you would say here is angle is sup to both of its consecutive angles, rather than memorizing that. The next one says show both pairs of opposite angles, and it has both. You cannot just do one pair. If you know that, then it's a parallelogram. The next one is the diagonals bisect one another. Show the diagonals, that's an A, diagonals bisect each other. And then the last one is show one pair of opposite sides are both parallel and congruent. If you show any of those, then they must be a parallelogram. These are all your ways to prove. It's like, how did we use to show that, prove that something was two lines are parallel? It was the converse of AIA, the converse of CAT, the converse of AEA, and the converse of SSIA. That was the way that we proved that just lines were parallel. Now, here are the ways that you could prove that a quadrilateral is a parallelogram. I hope that made sense. Come to office hours or come to class with questions if you have any. Thanks for watching.